Okay, welcome to one more video on memories. So in the last video we were discussing about DRAMs. So one of the DRAM that we considered was 3T DRAM. So using 3 transistor we could able to see how can we able to write the value onto the memory location and how do we read it. So the improvised version of the same DRAM is 1T DRAM. So 1T here stands for a single transistor is used to uh, store the value and then read the value from that particular bit. So let us see the circuitry for that 1T DRAM. So we will have uh, a line corresponding to word line, so and then we will have a bit line also, so as we usually have it for any memory location. Then we'll have only one transistor which is responsible for storing the value is connected to the word line and the bit line. And you can see now, since we have only one transistor which is being controlled by the word and the bit lines, which is being controlled by the word line, and of course it has been accessed through bit line. So we are going to have an exclusive capacitor that is fabricated, which is going to store the value that is supposed to be uh, read here. So this is the circuit of 1T DRAM. So as the name itself indicates that since it is a single transistor, this is the transistor which is being used to store the value, and of course which is used to help the store value and then to read the value. So this is not a parasitic capacitance, this is a lumped capacitance which is exclusively uh, fabricated to store the value of the bit that is supposed to be read. Now let us try to see how does this circuit will operate, because we know that this is the capacitor which is exclusively used to store the bit value, and of course this is one bit. Like such, n number of bits will be connected to this bit line, so that will going to have some capacitance for this bit line. So let us try to represent the effective parasitic capacitance of this bit line as CBL, which stands for the bit line capacitance. So let us try to understand the working of this. So under normal condition, supposing that this is the word line. So if the word line is 0, this MOSFET is 0. Let us assume that this is the voltage at X. So let us try to find out what is Vx is. If you assume that initially the voltage across this capacitor is 0 volt, if it is 0 volt, then you'll be having Vx as 0 when the word line is 0. So as soon as you make the assume that you want to make the word line as equal to 1. So suppose if you want to make a data 1 to be stored here, so before I want to store a data 1 here, so on the bit line, because bit line is the one where you can able to give the value, so that this value will be stored in this capacitor CS. So assume that okay, initially under normal condition this voltage of bit line will be VDD by 2. If at all if I want to store a value of VDD onto my uh, bit location, so let us make the bit line as VDD. Once you make the bit line as VDD, you make this WL as equal to 1. This is like okay, writing the value. So this is for writing the VDD value onto this capacitor. Because of this, capacitor now acts as a pass transistor, because this will be 1 and you have a voltage VDD here, then a voltage of VDD minus VTH will be written onto this Vx. So meaning, so once you make this VDD and your right line becomes, or WL becomes high, so this voltage at Vx will rises and then it goes to VDD minus VTH. VDD minus VTH, assume that this is also VDD. So now even if I make this equal to go low, so this has gone low, so even this has gone low. Of course, assume that now what you can do is you can make this again to come down to half of VDD, because the writing process has been completed, because write has gone, the word line has gone low, so you have actually written the value of logic high onto this capacitor. with a voltage equal to VDD minus VTH. Because the pass transistor, you're going to get a weak 1 stored in this capacitor CS. So this is the voltage across capacitor. Now this is VDD by 2. Now even though when you make this VDD by 2, okay, once as this turns off, as your word line goes low, this is off, the capacitor will not discharge. It doesn't have any path for discharge. Now it stays there in VDD minus VTH. Now assume that you want to again make this right as high. So this is again made high. The WL, that is word line, has been made 1. So when you are making this word line equal to 1, now it is the purpose of reading. Now I want to read what is the value that has been stored now. So before I make the read operation, as we know that the bit line will be always there at half of VDD. Since the stored value is VDD minus VTH, and you can see here you have assumed that VDD is equal to 5 volt and VTH is equal to 0.5. We have 4.5 volt stored here. Assume that BL is half of VDD, that is 2.5. The moment when you close this switch during the read operation, so we naturally know that there is a charge distribution that is happening, because you have 2.5 volt and 4.5 volt coming together at bit line. So what happens to this bit line is, because now this, as soon as the word line goes high, so as soon as the word line goes high, you can see this rises. So this voltage rises and naturally this comes down. So this why it comes down is this is going to lose the charge and this is going to gain the charges. So we know that this is going to go high. This is going to go high, and then this will settle down, and this has gone down, and then so this goes, because this has slightly discharged and then stays at a some voltage. Now this has risen and this is staying at some voltage. Now you can see you had 2.5 here at the beginning of your read cycle, and you had 4.5 here. After turning on this transistor for the read operation, so this voltage 4.5 has reduced and this 2.5 has increased. So now we should sense it. The voltage of your bit line will go greater than VDD by 2, since the stored value here is 4.5. So we are looking at whether the change in voltage, since the bit stored is VDD minus VTH, which is high value, the voltage at bit line immediately after this word line going high for this read operation has actually increased beyond the bit value, so beyond VDD minus VDD by 2. So we are now looking at what is the value of your change in the voltage on the bit line. So this is given by delta V is given by V of BL minus V of precharge. So this V of BL is nothing but voltage. It is voltage at BL after read operation. Once you actually make this equal to high, after some time the voltage will settle down here. So you're looking at what is the voltage of the bit line after read cycle. So after you read it, so what is the voltage, and V precharge is nothing but half of VDD. So we know that if the stored value is VDD, the bit line will be certainly higher compared to the precharge voltage. Since the precharge voltage is 2.5, the bit line will settle down for a voltage certainly greater than 2.5, because now it has to settle down between 2.5 and 4.5. The change in the voltage is positive. If the change in the voltage is positive, then we say that the value that is stored is logic 1. That is, if the delta V is positive, then we say that the bit stored is high. So when do we have this positive delta V? Means when voltage at the bit line is greater than the voltage at the precharge. This will happen if the voltage that is stored in CS is more compared to the precharge voltage. So we can also write an expression for the delta V in terms of the capacitance of your bit line and capacitance of this CS, can be written as V bit minus V recharge multiplied by the capacitance CS and CS plus C bit BL CPL. So this is an expression where you can able to also find what is the change in the voltage, where V bit is the voltage of your bit line. You can see now bit line is nothing but the voltage that you're going to, so it is that voltage. So now how much is the voltage that you're applying now? The bit line voltage is the voltage that you're applying here. So this is the voltage that you applied. So at the beginning of your bit line you applied VCC, and then pre-charge is actually 2.5. It is VCC minus 2.5 multiplied by the capacitance of this capacitor, the voltage that is the capacitor which is used to store the charge, and CBL. Usually the CS value will be very small compared to CBL, because CBL, why the capacitance is high means because like such type of hundreds of transistors will be connected to this, okay, something like this. You have one more bit, you have one more bit, you have one more bit. Likewise you're going to have hundreds of transistors. Naturally CBL is far greater than CS. CBL is greater than CS. So this ratio will be very small. So we will not be looking at, okay, whether what is the absolute value of your delta V. What we are looking at is this delta V, is it positive or negative? If the delta V is positive, then we think that the stored value is high. Stored value is high. If the delta V is negative, then the stored value is less. Meaning, since the pre-charge voltage before the read operation will be half of VDD, upon reading, if this voltage goes above half of VDD, then we assume that the stored value is 1. If upon reading, upon making this read is equal to, or the word line is equal to high, if the voltage goes low, then naturally the bit value that is stored is 0. Because when you have 0 here and 2.5, naturally the voltage here goes less than 2.5, then it can be easily understood that the bit that is stored is 0. So here we are not exactly looking into what is the magnitude of your delta V. We are simply looking at, is this delta V is becoming positive or negative. So using sense amplifier, suppose you find that if the voltage is becoming positive, then you say, or if the change is happening in the positive direction, then you immediately say the value that is stored is high. If the reverse is happening, then you say the voltage that is stored is 0. The major disadvantage with these type of DRAMs is that after the read operation, whatever value that you have, you can see this actually destroys this, actually, because when you make this equal to when you make this turn down, whatever charge that is there, that will going to redistribute, and you cannot say what is the value after once you read the operation. That's why usually whenever you're using the DRAM followed by read operation, you are supposed to have a write operation. So read is always followed by a write operation. Assume that you are actually stored a value of high here. Logic 1 is stored. So upon reading the value, this voltage or this charge will be get distributed, and this is going to reduce. You cannot read this again. If you want to read this again, first you have to write that earlier value of high and then read it. And if you don't read it for a long time, there is a possibility that you may lose the charge. So naturally, after every read operation, we have to do one write. If you're not reading, you have to at least keep on writing a number of times within that interval, so that the value that you are intended to store is there intact in that particular capacitor. So this is one care that should be taken whenever we are using DRAM. So repeated writing operation is required, and even whenever you actually do one read operation, write is a must. Otherwise the value will not be properly stored, or the value will not be stored in that exact particular location. So this way we can able to use a single transistor for its operation. Of course, we have to also ensure that okay, this CS. So if CS is smaller means okay, you can still achieve it at a very lower dimension. So CBL is naturally higher. So looking at all these values, so we can able to consider whether the bit that is stored is logic 1 or logic high by looking at the output of the sense amplifier.